Thank you for coming. My name is Vittorio Romeo, and I am a student, a computer science student from the University of Messina in Sicily, and a C++ enthusiast. Today I'm going to talk about a very interesting code snippet that was originally posted by Sean Parent on Twitter, and it is actually this tweet right here. How many of you are familiar with this tweet? All right, so it's a very cryptic piece of code that actually executes a callable object on every passed argument. Other than analyzing this code snippet, we're actually going to expand it and have it allow usage of generic arity functions, and also take a look at C++17 fold expressions and make vector and make unordered map functions that will actually deduce the type of the containers from the passed arguments. So let's begin by showing you a simple example. This is the code from the tweet, just copy-pasted. And this is how it works. We call for each argument with a callable object, in this case a lambda, generic lambda here, and some amount of arguments, any amount of arguments. They don't have to be the same type, they can be any kind of type. And if we run this code segment, we see that we get the expected output. And what it does is practically call that lambda, passing every single argument as the argument of the lambda. That's basically it. So it's hard to understand written in that way, but if we actually rewrite the function and try to understand what's going on, it's actually quite simple. So the first thing that's actually strange is this initializer list here of int that gets casted to void and returned. This is here because we need a context where we can expand our variadic template arguments using the ellipsis operator. As you can see in the signature of the function that I've renamed here, we're passing a function, any kind of callable object by forwarding reference, and any amount of parameters using a variadic template. We can actually expand this back only in specific contexts, such as an initializer list or a C-style array or a generic variadic lambda. So using an initializer list or a C-style array guarantees that the order of the arguments is actually expanded from left to right. The first iteration of this snippet posted by Sean Parent actually used a generic lambda, and that doesn't guarantee the order of evaluation. So this is why we have the initializer list. Now, as you can see, this big piece of code between the round parentheses is what is going to get expanded from this ellipsis operator. So we're going to expand this a number n of times. That's the same number of arguments we're passing to the function. And inside this piece of code that is going to get expanded thanks to the ellipsis operator, we're actually calling the function, our callable object, and forwarding one of the arguments of the pack. Now, since this is an initializer list of int, we actually need to make this whole expression evaluate to an int so that it can be expanded and compiled from inside this initializer list. So we just use the comma operator here to evaluate to an int. And that's basically it. This is very simple when you look at it this way, but it's very powerful. So if you're still a little confused, this for R's call, which is the same as the previous example, roughly expands to something like this. It's an initializer list of int, and this is the parenthesis that gets expanded with the ellipsis operator. And every time we expand a single argument, we're repeating the function, we're passing the argument to the function, and we're using the comma operator to evaluate to int. And all of this is roughly the same as writing this piece of code. So it's a compile time expansion with no kind of overhead. It's very powerful. And this is the same example, so there's no need to run it. Let's move on to the second example. So this is the function without any comment, but with some formatting and white space. It's very clean in this way, and you can see actually what's happening. So what is this useful for? One example idea is creating a make vector function. So like make array and other make underscore functions, this will actually not require the user to specify the type of the items. It will deduce the type of the items from the items themselves. So the first problem we have is that we need to deduce what type of container of vector we're actually going to return. And to do that, we're going to use std common type t. So if you're not familiar with this underscore t syntax, it's basically C++14 introduced many versions of the original type traits functions ending with underscore t to avoid using type name : type. It uses the using syntax from C++11, and it's just a way to avoid writing colon type at the end. That's very noisy in terms of syntax. So this is what you would write using C++11. You needed type name and colon type, and now you can just say add pointer underscore tier, and it's the same exact thing. So it's just syntactic sugar. So we can use common type t to actually get the correct type that we're going to return inside of the vector, and we can instantiate the vector with vector item, which is a type alias for the common type. Now, since we know how many items we're actually going to construct the vector with, we can just reserve the memory in advance. So this is a small, nice optimization. And we can do that using the size of ellipsis operator, which returns the number of variadic arguments passed to the function. Now we actually need to emplace back the items into the vector, and that's where forArgs comes into play. We simply use forArgs to iterate over the passed arguments, which are forwarded here. And our callable object is a generic lambda taking a generic x by forwarding reference and capturing the vector, and it's going to emplace back the forwarded argument inside the vector. Everything clear? Okay. And then we just return the vector. The cool thing is that we can now just say auto, v0, for example, make vector with some arguments, and it will deduce the type itself. So this is roughly equivalent to writing a std vector of int, reserving the memory, and then placing back the numbers 1 through 5. So that's it. We can statically assert that the correct vector type is being returned. In this case, it's vector of int. And we can do that with other types, for example, with constchar star, and it's going to get the correct type as well. And if we mix type like std string and constchar star, basically std common type t will actually deduce the most common type by checking the possible implicit conversions. So the type that can be converted to all the other types is the common type. And that's basically it. So let's just compile this segment to see the output. As you can see, we get 1, 2, 3, 4, 5 from the first vector here. We get hello everyone from the second vector. And we get hello world from the third vector. So before moving on and implementing more interesting stuff, we need to digress a little and cover compile time integer sequences. And this is a feature that was introduced in C++14, and it will be very useful for the next code segments. So when writing template code and metaprogramming, it's very useful to have contiguous compile time integer sequences because you often want to access arrays and tuples using metaprograms, so a compile time. And C++14 actually standardized this into a type called index sequences that can be generated using std make index sequence. So if we say using seq0 equals std make index sequence of 10, this will actually construct a type, a list of indexes that goes from 0 to 10 non-inclusive. So it's a compile time list of numbers that goes from 0 to 10 non-inclusive. This is useful because we can actually specialize our templates to match the index sequence so that we can actually expand using the ellipsis operator every single index. And this can be used to actually, for example, print an index sequence using forArgs. So if we if we forward declare a template struct here that takes a single type, and if we specialize it with a variadic size t template that actually matches an index sequence containing those indexes, we can actually print the index sequence by expanding inside our forArgs function the sequence itself, which is actually a variadic pack of arguments. So by doing that, we can just call seqprinter with our previously alias said seq0 and call print, and it will actually print the number from 0 to 9. So let's try it out. And as you can see, it works. We can also avoid using like an alias and just call it make index sequence of 5 directly into the seqprinter. So as you can see, it works. This is a very powerful feature, especially when dealing with nested index sequences, and we'll see some of that in the next code segment. So what we want to implement now is a function that will allow us to iterate over std tuple elements. So it is heterogeneous iteration over std tuple elements. To do that, we actually need another helper function that will be standardized in C++17. It's called apply. There is a proposal by Peter Sormelad, which is here at the conference, which gives us a very basic implementation, and they've roughly followed the proposal to implement it. So it is composed by two different functions. We have an implementation function called applyImpl and an interface function called apply. The interface function takes a callable object and a tuple, and what the semantics of the function are that the elements inside the tuple are unpacked and passed all at once to the function. So we'll actually rename std tuple with the name of the function and call it with all the arguments at once. To do that, we actually need an index sequence that will go from 0 to the size of the tuple, so that we can use std_get with the ellipsis operator and get every single element of the tuple. After calculating the index sequence here, we call our implementation function, forwarding our callable object and forwarding our tuple, and actually creating an instance of indices that will be matched not by a template specialization, but by an overload. So we can actually get the inner index list in this other method, this other approach, which is also very nice. After we actually unpack the indices, we can just call std_get with the indices for every element of the tuple here. And all of this is going to expand to std_get from 0 to the size of the tuple, so all the elements of the tuple. And we can just call the function with this ellipsis operator inside. So what we're actually doing is unpacking the values of the tuple inside the function and calling the function. And this will be standardized. It is already available in this std experimental namespace. So now we want to iterate over the elements of a tuple. And to do that, we can actually mix our apply function with our forargs function. So this is quite interesting. What we do is we call apply, passing this lambda here, this generic lambda here, as our callable object, and our tuple will be forwarded to apply as well. So we unpack the elements of the tuple inside a generic lambda, generic variadic lambda, taking any amount of arguments that will forward the arguments to forargs alongside the original callable function. So what we're doing here, we are unpacking the values of the tuple inside forargs. Forargs is going to get every single value of the tuple and forward it to our original function. And this will actually allow us to iterate over tuples with a very convenient syntax using a lambda, generic lambda. So it's a very simple implementation. As you can see here, if we call for tuple with a generic printer lambda here that calls std_cout and std_make_tuple, what's actually happening is this function here, this printer function here, is getting called with then with hello, then with the 15f float, and then with c. Not all at once like apply, but element per element. So we're actually iterating over the tuple. So this is roughly equivalent to writing this function here, which is forargs, with every element of the tuple. The thing that for tuple is doing is actually unpacking the tuple elements inside of forargs. So we get tuple iteration. If we compile this code segment, as you can see, we get the expected result, and it's pretty useful. If you didn't use this kind of approach, you would have to use compile time template recursion, but nowadays we have Boost HANA, so just go use Boost HANA. So now we're going to implement something very interesting, but also very complex at first. So forargs is very useful, but it is limited to unary functions. What if we want to actually define the arity of our function as a template parameter? We can actually do that, and this following implementation was written originally on Stack Overflow by Daniel Frey, and I've cleaned it up. So what happens here is that we actually need to forward declare an implementation function for our for_n_args function, and the main for_n_args function will be called by the user with an arity parameter that will be actually defined by the user, and obviously we will pass a function and a number of arguments. We will start by aliasing the number of arguments here using the size of ellipsis operator. And we actually need to statically assert that the number of arguments is divisible by the arity, because we want to call the callable objects with arguments in groups of arity per arity. So if it isn't actually divisible by arity, it is impossible. We will have some extra arguments that will not get called. So we call the implementation function with two different index sequences here. The first sequence will actually be from 0 to the number of function calls that will be executed. So if we have like 10 arguments and we're going to call a binary function, this will go from 0 to 5, because the binary function will be called 5 times, and every time we'll use 2 arguments. The second index sequence will actually go from 0 to the arity of the function, and this will be used in the implementation function to actually get the correct parameters. The implementation class has a static exec method that will actually require the callable object and all the elements forwarded as a tuple. This will actually get optimized by the compiler, so there's no actual overhead here. So remember, we're passing these two index sequences, the function and a tuple containing all the arguments that we pass to the interface function. Now we can define our implementation function, and we actually specialize over the index sequences. So I've called the first one tn calls, because it's the number of function calls that will happen. And the second one is tn arity, because it's just from 0 to the arity of the function. The static exec void will take the tuple by const reference, and it will use the expansion idiom using not an initializer list, but a bool C-style array, aliased to swallow for readability. And we actually do what we did for args. We cast it to void, and inside of this context where ellipsis operator expansion can take place, we repeat this expression here a number of times equal to tn calls. So we're actually calling our function tn calls time in here. This will get expanded 5 times if we add 10 arguments and a binary function. So here's an example to understand what's going on. If we add this binary function called fn, and we call for an args with an arity of 2, passing the function and then 4 parameters here. As you can see, they are not in STD pairs or in groups, they are just parameters. And what's going to happen in this expansion right here is that for every call that needs to be made to the function to actually swallow all the arguments passed to the function, we're going to call execn with the index of the function call multiplied by the arity of the function defined by the user. And we're going to pass the function, our callable object, and the tuple of the elements that will actually be forwarded as a tuple. Then we actually use the comma operator to make the expression evaluate to a valid Boolean, so that the compiler will not complain because we're using a bool C-style array. So as you can see, we have 2 calls to execn. One will be called with 0, and one will be called with 2. And those are actually the starting indices of our arguments. So inside execn, we will start from 0, and we will go from 0 to arity, which was 2, and actually get the first and the second arguments. In the second call, we will start from 2 and get the third and the fourth arguments. So this is the execn function, which is another implementation function. And this is where we actually call our callable object using stdget of the base size t template parameter, which is actually this number here. In our example, it's 0 or n2. And we're going to add that to the arity. So it goes, so it actually takes the correct parameters. So again, to understand what's going on, take a look at this example expansion where we actually call the function again with 4 parameters and arity of 2. And this first expression here that is in the exec function will get expanded to this. And as you can see, we're actually getting the argument at position 0 and the argument at position 1, so 0 and 10. And this expands to a call to a function with 0 and 10. And the second expression here will actually expand to a stdget of 2 plus 0 and 2 plus 1. So we're actually getting 20 and 30. And this will expand to a function call to 20 and 30. So this is actually doing what we want. This is grouping the elements together, the arguments together by arity, and passing them not one at a time, but n at a time to the callable object. To see an example of this in action, if we call for n args with arity 2, and we pass a binary printer function here that will actually print the product of 2 numbers, and pass arguments like 21, 22, 23, and 24 without any kind of explicit grouping like std pair or an initializer list, it will actually do the right thing and group the arguments together at compile time. So if we actually execute this code segment, we can see that we actually get the correct products of the number. We passed 8 arguments to the function, but we are only getting 4 because we define the arity as 2. We can do the same with any arity because it is a template parameter. So in this case, we have an arity of 3. And we're actually passing a lambda here, generic lambda here, that will sum the arguments together and print out the sum. And passing arguments in groups of 3 here, like 1, 1, 1, 2, 2, 2, and so on. And as you can see, we get the expected result here. So this is interesting. And let's see a possible use case in the next code segment. Is everything clear so far? Any question? OK. So a possible use case for this will be shown in this code segment, and we're actually going to implement a make unordered map function. Like the make vector function, this one is not going to require the user to explicitly say the type of the map. It will infer the type of the map from the passed arguments. So the first thing we have to deal with is defining some kind of helper that will allow us to figure out the common type for all the keys and the common type for all the values of the STD unordered map. To do that, we're going to use C++ 14 index sequences to divide the passed parameter pack types in 2 different packs. So if our types, the arguments will be passed all at once. So we actually want to get some sort of checkerboard pattern here, where our first index sequence will actually get all the keys. So this will be the indices that we actually want. And the second index sequence will get all the values. After having those sequences, we can actually call std common type t on those specific subsequences so that we can get the common key type and the common value type. And then we can instantiate the map. So to do that, we're going to define a struct called common kv helper that will take a sequence and a number of arguments. And basically, the sequence will go from 0 to half the number of arguments. And it will figure out, using simple arithmetic and ellipsis operator expansions, what the common type of the keys is, and the common type of the value is. So as you can see here in the implementation, we match against the index sequence. Remember that the index sequence goes from 0 to half the number of arguments. We assert, obviously, that it is divisible by 2. And now we're going to use std tuple element t to actually get the nth type of the variadic pack, which contains all of our arguments. So we define a simple alias here, taking the index as a template parameter, which is a simple alias for std tuple element t that will actually wrap all of our arguments inside an std tuple, and this is actually equivalent to the nth type of the parameter pack. And to get the key type of all of our arguments, we will call std common type t using type at the index sequence that goes from 0 to half the number of arguments multiplied by 2. So this basically calls common type t on all the even parameters that we're passing to this helper class. For the value type, we'll do the same thing, but actually call it with +1 here. So this will actually get all the odd indexed types of our arguments. So that in this way, we can figure out the common key type and the common value type. Again, an example expansion of this is for 3 generic arguments, is having the key type here being expanded with 0, 2, and 4, so all the even indices, and the value type with 1, 3, and 5. And since this is common type t, we can use this to instantiate our map. So we're going to actually define some aliases here just for syntactical sugar that will actually get the common key type and the common value type from the list of all the arguments. And we're just going to make some little tests here with static assert. So if we have a parameter pack with 2 types, the first type will obviously be the key, and the second type will obviously be the value. And as you can see, the tests pass correctly. And the power of this is that you can have any number of parameters without any kind of explicit grouping, so no std pair, no std tuple, and it will actually figure out what the keys are and the values are based upon the position of the arguments inside of the template parameter list. So in this case, if we have std string int, std string float, const sharp pointer and long, it will actually deduce that the key type is string, and it will deduce that the value type is float. So we can finally implement make an order map. It will alias the common key type and the common value type, and it will use them to instantiate an unordered map called result Again, we actually know how many items we're going to have inside the unordered map, so we can reserve the memory in advance as a small optimization. And now we can use for n args with a binary arity, and our callable object that will be called for every group of 2 arguments will be this generic lambda here that will actually forward the key and the value to the map as a place member. So this is actually emplacing both the key and the value. And then we just forward our arguments to the for n args function. So an example usage of this make an order map function is shown here. As you can see, we have this m, and we're actually using string literals here. This is an std string with value 0. This is an std string with value 1, and this is a normal C-style const_char string with value 2. And here we have some numerical values. If we call make an order map and then static assert the type of the key and the value, we can actually see that the correct type is deduced, and we have string for the key and float for the value. So this can be useful sometimes where you don't want to explicitly have the user decide what type the map should be. And as you can see, we can just run the code segment here, and it will print 0, 1, 2, which is the expected result. So how much time is left? Okay, we have time to quickly look at fold expressions. So everything is, sure.
Question. Why didn't it print out like 1.0, 2.0, like in the output for that?
Sorry?
If you go to your console,
yeah.
Why didn't it print like 0.0? Like why aren't those printed as floats? Why is there no decimal? Yeah, why is there no decimal? Maybe it's a dumb question, but
I'm not sure, actually. So the question is, why aren't the numbers printed as float here? Well, we are sure that they are actually floats because we statically assert that the type of the map value is float. So it has something to do with stdc out. It's not part of the. So let's briefly look at fold expression. So everything you've seen here will be useless in C++17 because we have fold expressions. And an example of that is a compile time way of checking if compile time Boolean values are true. This is a C++14 implementation where we actually need compile time recursion and integral constant to check if all the past integral constant bool values are true. And as you can see, this gets quite annoying because you need a base case struct and a recursive case struct to deal with the recursion. But it works. But in C++17, we can just use fold expressions, which reduce the amount of code to just this line. So what fold expression actually do is they take a parameter pack, an operator, and optionally a base value, and they do a fold operation over the parameter pack and the operator with the base value. This is a concept very often used in functional programming, and it is roughly equivalent to having recursion and actually passing every single element and calling the operator between the previous element and the current element. So it's just folding all the parameters with a single operator into a single value that will actually be the result of our computation. So we can use fold expressions with a set of operators that the standards gives us. And one of those operators is actually the comma operator. So we can actually re-implement for each argument the one unary function with a simple fold expression here. We just call the function with the parameter pack, the comma operator, and the ellipsis operator. And this will actually do what we implemented with for each argument and what was in Sean Parent's Twitter. So that's the C++17 way of implementing for each argument. What about make vector? So we can implement make vector just like this. We get the common type t of the parameter pack, we reserve the memory, and then in round parentheses, we have the expression that we want to be repeated, which is and placed back with every single element of the parameter pack. We just put the ellipsis operator here, and it will actually do a fold over the comma operator, and this is make vector. So as you can see, it's 3 lines of code. Very simple. What about the non-unary for n-args? So the implementation is a lot simpler than the previous one, but I'm still sure it could be improved. What we actually do here is we have a 3-step implementation. The first step, that is actually the deeper step inside of our implementation, we'll actually call the callable object getting the correct elements from the forwarded tuple. If you remember in the previous implementation, we were passing all the arguments inside of a tuple. And this will be as simple as using std_get with the start index and the index that represents the arity of the function and the tuple. So it will actually call the function with an amount of arguments that's equal to the arity. The second step will actually use a fold expression over the comma operator to call this third step here for an arc step using a sequence that goes from 0 to the arity. And here we'll actually multiply the amount of function calls by the arity, as we did in the previous example, and actually passing the sequence that we're going to use with std_get as a value here so that we can get it as an overload and unpack the indices inside of it in our third step function. And as you can see, we don't need all that compile time recursion that we had in the previous implementation. We can just fold over the comma operator, and that's the same thing. Now in the interface function, it's very similar to the one in the previous code segment. We just forward the arguments as a tuple, and we pass this tuple for an args expansion with the desired arity, and that's basically it. So some examples here, very simple. For example, we are using for an args with an arity of 2 here to our print wrapper, which basically just prints the arguments, and it will print the arguments in groups as expected. As you can see, 0, 1, 2, 3, 4, 5, and 6, 7. And the same with an arity of 3, and it will print the arguments in groups of 3 here. So that's basically it. Thanks for attending. If you have any question, I'm happy to answer.
I think we're out of time.
OK, so we're out of time. Find me later if you have any question.